I'd like to thank Gabby and the local organising committee and the ANZSNM Scientific Advisory Panel for inviting me to deliver the Pioneer Lecture. It's a great honour. After the excitement of being asked to equilibrated, it occurred to me that invitees are generally towards the end of their career, maybe getting the wind up from the profession that it's time to consider retirement. But retirement will have to wait because it's an exciting time for nuclear medicine with the re-engineering and re-emerging of some of our capabilities. ANZSNM 2019 has a conference theme of precision nuclear medicine, and in many ways precision nuclear medicine celebrates the unique capabilities of nuclear medicine to improve patient outcomes. It heralds a new era and opportunity for all the ANZSNM professions. While we're all central parts of the precision medicine landscape, many of us don't understand the language. Today I'm presenting an insight into radiomics, artificial intelligence and neural networks, and the role they play in precision nuclear medicine. Some may think this is an emerging area, but it's an exciting domain that is already entrenched in nuclear medicine practices, and we need to keep pace or be left behind. Internationally, radiomics and artificial intelligence are streams in major conferences in nuclear medicine and radiology, and domestically it has been the focus of entire radiology conferences like the 2019 RAD-AIM conference on the Gold Coast. Radiomics and artificial intelligence will be included in the 2019 RAINS conference in November in Sydney, and the theme of the pre-conference symposium at the ANZSNM 2020 in Sydney. So in some ways, this presentation is a bit of a taster. This presentation also aims to connect the dots and at the same time celebrate the nuclear medicine industry itself as a silent pioneer, having built a culture around radiomics, artificial intelligence, precision nuclear medicine for many decades. They're embedded in our culture throughout nuclear medicine and molecular imaging, even if the names are new. We've provided the foundations on which others can build, and we can extend, which we must do or we'll get left behind. So just a brief overview, I'll cover radiomics, artificial intelligence, neural networks, provide a simple case study, and then look at future opportunities. So what is radiomics? Radiological genomics is just an abbreviation. We've heard of proteomics and genomics. And so we're looking at how the radiological imaging provides that unique and in-depth insight into patient care. And nuclear medicine is included in that. It's more than just quantitation, and we've been doing it for a while in nuclear medicine. So we actually have some very rich resources in quantitation in nuclear medicine, but some of our things go beyond that if we start thinking about, even in the old days when we're looking at phase analysis and stroke images on our gated heart pull scans. It extracts and analyzes advanced quantitative image features, and this is actually fairly unique to nuclear medicine over a long history, whereas in radiology it's something that it's actually redefined as radiomics because it's something that's new, that they're looking for more than just what they're seen on the screen. They're looking for additional features that they can analyze and try to actually get an insight into patient outcomes. It's the conversion of images to high dimensional data, and subsequent mining of that data to improve decision making. So mostly we hear about radiomics around CT and MRI and the additional features beyond what's seen on the screen that can be extracted. But SPECT and PET have been doing it for years. It's not just what's seen on the screen. The physiological and the biological nature of the nuclear medicine images lends itself to that feature extraction. It can create larger mineable databases, which is really important, and I'll discuss that a little bit later. And it includes things like image acquisition and reconstruction, image segmentation and rendering, then the feature extraction itself, and then quantification of that, the data sharing and databases, and informatic analyses. So just a quick schematic from Alana Vile's paper, and Alana will be speaking at the 2020 ANZSNM conference in Sydney. And so if we look at this CT image on the far left, it's the first part of the imaging process. So obviously it's a CT example, and there's a mass in the lungs, and traditionally we'd look at that mass, we'd measure it, you'd be able to see its dimensions, and we do that through via segmentation. So in segmentation, which is common when these are being converted for radiotherapy, you can actually see a region of interest is being drawn to define that in a 3D volume and 3D space. And what that then allows is to go beyond that. Radiomics is then going beyond that to actually start to think in that 3D space what the tumour shape is, what the tumour intensity is, and then to try to quantify in some fashion the actual texture of the tumour. So you can imagine that these feature extractions we take for granted in nuclear medicine. Something as simple as SUV is giving us information about tumour intensity, or is at least the substitute thereof. And that allows us to actually do some analysis. In this case, an ROC curve at the bottom, and then survival curves at the top. So the way that I look at this scenario is putting the patient in the middle. So if we put the patient in the center of our domain, what are we actually doing in nuclear medicine? And so I don't think that personalized medicine is the same as precision medicine. Personalized medicine to me is patient facing. So we look at little data, or, as opposed to big data. Whether it's a diagnostics and therapeutics, it includes the patient's history, but it also includes the patient narrative. And so you actually end up with patient-facing care and patient-facing decision-making. That can feed into evidence-based medicine, and so then we have this evidence-facing patient care model. But precision medicine, to me, we're looking at early diagnosis, optimization of therapy, and prevention, looking at the patient as an individual, but looking at those characteristics and features of that patient or their disease. The list of the omics, genomics, proteomics, etc., the combination with radiomics for nuclear medicine in particular, but CT and MRI, and then integrating that in some fashion with machine learning or artificial intelligence that dovetails into big data. And for us, the big data might come from ARTNet or MSAC, and that allows us to actually use these neural networks or artificial intelligence to have this deeper understanding that then further drives precision medicine. And so in the end, we actually have the patient-facing, the evidence-facing, and then the pathology-facing patient care that drives improved outcomes. And from there, we can actually do some learning. So what do we do in Australia? My view in Australia is that we actually get most of that right. With precision medicine, we do precision nuclear medicine very well, in my view. There's a question mark on that because I think we can do it better, is if we actually engage with the radiomics and the machine learning, then I think we can actually enhance precision medicine even further. We do a question mark on big data because we have some big data through ARTNet and MSAC and other things, but we don't actually have a formalized process for communicating that, and there's a few challenges that I'll talk about in a second that don't make it a national kind of data collection. But what we're not really doing in a big way is looking at that deeper learning using neural networks to enhance that decision making in precision medicine. So what are the challenges for radiomics in nuclear medicine? There's variations in acquisition and reconstruction protocols for everything from matrices or matrices and slice thickness, orientation, positioning, filter types, uptake times, and then the CT and the MRI aspects of things. CT is fairly simple, MRI is more complex, and SPECT and CT, SPECT and PET are fairly easy to standardize, but we don't. There are variable protocols across the nation. Large patient data sets cost time to get rich insights. We don't actually use that, and it's not part of standard care. So for example, is that we'd get a much richer big data set if we did list mode dynamic uptake phases on every PET patient, but we don't have the time and the resources to do that. So standard care doesn't lend itself to actually those big data sets of really rich information. And of course, ground truth, what is the gold standard, may differ. There may be some variations, inter-operator and inter-reader variability. Segmentation can be challenging, and I'll show you an example of that shortly, especially in large or complex anatomy, and there's inter-operator variability associated with that. And then there's the impact of noise on automated segmentation. So here's an example from 2013. It's a test-retest inter-observed variability study using PET fused to CT. So you can see on the left, diagram A, we can actually see a mass, and we can actually use some automated segmentation of that to then extract some features, and those features will be radiologic as well as nuclear medicine, and they can then drive some form of analysis. So if we look at the data, the test-retest of tumour volume from baseline to follow-up had a 71% agreement. Not great. Okay, so between baseline and follow-up, there was a variation of there was actually 71% agreement. So we've got a 29% variation on that. Perhaps more importantly, is that while the number looks good, the inter-observer reliability was 91%. When they actually had 5 independent operators that did their tumour delineations, then these are the 5 regions that they end up. This is just one example of the tumour, and 5 very, very different regions. And you can imagine in nuclear medicine that that's what our SUV is going to be calculated on. Our maximum is going to be in those ranges somewhere, and our mean is going to be calculated based on the entire region. And so it actually makes a bit of an argument for blending that segmentation process with artificial intelligence to try to get some degree of consistency. There's also no consensus on the performance metrics for segmentation and then extraction of data, the accuracy, the reproducibility, and the consistency. Data sharing and de-identification creates some issues, including privacy. How do we share that information? What are the ethical consequences of that? And so developing cross-modality radiomic analysis toolkits, so we're actually doing the same kind of tools and the consistent information, same regions between our MRI, our CT, our PET, our SPECT, but we should be looking beyond that, including planar images, and how do all of those correspond and work in a cross-modality fashion. And then of course you've got to have validation of those biomarkers. And so if we think about the features that are extracted for precision medicine, tumor intensity histograms, right? So the HU, mean, median, maximum, minimum range, and skewness associated with CT, but we already do that with SUV. So for us, SUV is part of those radiomic extraction processes in terms of features. So when we don't think radiomics applies to nuclear medicine, it does. SUV is part of that. The shapes, the geometric shape, the total volume, the total surface area, the surface to volume ratio, these are things that are extracted from an anatomical perspective and then co-registered with our physiological imaging. And of course there's concepts in terms of texture, and texture includes our radiological imaging as well as our physiological imaging. So probability, density function, contrast, correlation, cluster, prominence, cluster shade, energy, homogeneity, maximum probability, sum squares all the way through to entropy and beyond. So how do we select those features? There's such a big range of features that if you're the person that's going to be interpreting this data, how do you actually work out which one of those features has the most importance, the least importance, and anywhere in between? Which features do you take notice of? And so without big data and neural networks, it's actually very difficult for us to actually adequately use that radiomics to actually enhance precision medicine and precision nuclear medicine. So in radiomics, we have a heat map, and the heat map just helps us. I'm only going to explain this because it pops up in almost every publication. They'll show you heat maps, but it helps us to understand what we're actually doing in terms of feature selection. So here's a paper that had 219 tumor features. So extracted from the data, 209 separate features. How do you try to actually make sense of 219 features for 235 different patients? So across all tumours, you can actually compare each individual feature using regression analysis, and you end up with an R-square plot. And essentially, areas of high correlation show up as red. And so I'll show you the map. Is that this is just an example of a map. And so you can imagine if there's along the x-axis and the y-axis has every one of those 200 odd features plotted against each other. So the first two on the list are actually obviously the same feature, and so you're going to get a perfect correlation associated with those. So it makes sense that your heat map has this red line down the middle that correlates with perfect correlation between those sets of features. And what it then allows you to do is actually look at those other features. So those areas of red which indicate high correlation show areas that actually are groups of features that have similar characteristics, and as a result have similar implications. And you can see down the sides on the other side that some of these are grouped. So in the pink we actually have a grouping of similar features that have high correlation. In the blue, the light blue, the green, the yellow, and the red down the bottom. And what that indicates is that amongst those group of features that have these high correlations indicated by the heat map, then we're actually going to weaken the data set if we include consideration for all of those features. So if feature 1 has an error of 10% and feature 2 has an error of 20%, but they correlate very closely together, well then when you actually include both of those features in your decision making, then you actually end up with a bigger error than if you actually just included one of those in the decision making. And so part of the heat map and then a part of artificial intelligence is helping us to select those features that allow us to actually reduce that error, and as a result maximize the amount of information that we have out and the accuracy of that decision making. I hope that makes sense. So radiomics and precision medicine, obviously just a quick schematic diagram. You've all seen this diagram or similar before. So on the left we've got our images, it's the starting point, we've got our CT, we've got our PET, we've got our MRI, and that actually has some sort of features and contours. So we do our actual segmentation to draw those regions, and then from that we need to extract those specific features around shape and texture and of course those functional type things like image intensity or density maps. The next part of that is to actually, obviously in between there, we need to decide which features we need to consider. And so we need to look at the associations, the tumor response, the tumor evolution, to see what occurs based on each of those different features, and then consider that in the decision making process, and so you end up with a goal of optimized treatment for the patient and precision medicine. So just to clarify, just because I'll use this language shortly, is that the radiographic features are divided into two parts. And so we're going to talk about the semantics and the radiomics. So I've spoken a lot about the radiomics, which is that quantitative type data that goes a little bit beyond what we normally do with quantitation in nuclear medicine, looking for those deeper things, but also linked to our radiological imaging. That's what we're going to call radiomics. And then we need to recognize that there's a whole bunch of other stuff that you might want to call qualitative, but it's really semantics. It's more than qualitative, in my opinion. And that's what the nuclear medicine physician or radiologist is considering. So the semantics is those aspects of an image data set that might be considered in the decision-making process by the physician or radiologist under normal circumstances. And it can include some of the normal quantitative information that you might get, like a left ventricular ejection fraction. But it doesn't include those deeper radiomic types of data. And so then combining the semantic information with the radiomic information gives us our strongest outcomes. And so how do we use radiomics? I've already mentioned that SUV, by its very nature, it describes quite nicely as a radiomic feature. But if we go back even further, I've already mentioned at the start of this presentation the idea of the phase and the stroke images on those original gated heart pool scans that we did. And this is the quantitative softwares from Cedars-Sinai, and of course the phase histograms on a SPECT blood pool study is a radiomic feature that could be extracted, along with those other things like peak filling rates, peak ejection rates, more so than the left ventricular ejection fraction itself. And probably one of the common areas that we actually have seen radiomics and artificial intelligence, for that matter, is actually in our software for our myocardial perfusion SPECT studies. So we've had our QGS and our SQL and a raft of other commercial software packages that extract things via polar maps, and they do, I guess, a segmentation in terms of segments of the heart, whether it's 17 or 21 segment model, and then it actually has defect scoring, it has reperfusion, reversibility, it actually determines scar and other predictive capabilities. So these are all some forms of radiomic extraction. And of course, a number of commercial suppliers of software that is designed to enhance radiomic feature extraction in our imaging. This is just an example from GE Healthcare that is designed to actually enhance in neurological imaging, co-registered between anatomical and physiological imaging extraction of radiomic features. It's not the only software that's available. There's a lot of commercial suppliers that actually have just these add-on software programs that are designed to draw out additional radiomic features. You've still got to decide what you do with that information once you've got it. And so this is again from GE, which is designed to extract additional information from lung scanning. So a quick snapshot. Out of Japan, we've seen FDG PET-CT radiomics used to differentiate pneumonia and lung cancer with an 83% extract accuracy. Johns Hopkins used radiomics in myocardial fusion SPECT to enhance prognostication and then predict the calcium scores. Out of the Netherlands, they showed radiomic features in gallium-68 octreotate being highly reproducible, and higher order radiomic features they felt were worth investigating further. Out of the Mallinckrodt Institute of Radiology, they reported radiomic phenotyping of brown adipose tissue, which was then able to successfully discriminate in clinical case studies brown fat from pathological uptake of FDG. So for me, probably the greatest value of radiomics is going to be in those higher order studies. We have some good quantitation of our lower order studies, our planar and our dynamic images, but those higher order studies in SPECT and PET, I think, will have the greatest value from radiomics. One of my PhD students out of Canada did some radiomic type work. Certainly used radiochemic feature extraction in CT planning using planning CT and cone beam CT, and the idea was to optimize the planned versus the delivered bladder dose, and essentially because the bladder volume changes during the course of a treatment, let alone the cycle of treatment. And so it used dose volume histograms and slender organ at risk pelvic IMRT, and we just see some of the data on the screen there. And then another Canadian PhD student of mine was actually using various imaging technology, including ultrasound, CT and MRI, to look at 2D and 3D imaging features. So doing feature extraction to identify plaques that are at risk, so vulnerable plaques. And then we actually did some data mining in small data rather than big data, but in a large data set out of Indonesia, looking at myocardial fusion SPECT in diabetic patients for predicting major cardiac events. And again, we're looking at a very large number of features that were extracted from that data set and then analysed in what we would call a manual way. And so for me, the next step is to say, well, how do we do that in an automated way and using an artificial neural network to enhance that? Which brings us nicely to artificial intelligence. And so artificial intelligence relates to computer algorithms that complete tasks usually associated with human intelligence. So they learn or they problem solve. It's been around for a long time. It's been used in movies. It's coined back in 1955. We all have a bit of a sense of what artificial intelligence is, and it impacts on lots of aspects of our life. But in health and medicine, and in particular nuclear medicine, what we're looking at is that this machine learning or deep learning capability, which I'll talk about in a second, and the capacity of computers to exhibit or simulate intelligent behavior. So we want it to be able to do things that would take us a long time to do, and we might lack the concentration to do it as well. So a neural network itself is an image analysis algorithm. It's composed of a number of layers, and you can define the layers depending on what the structure or the architecture that you want to use is. And so it's meant to be a little bit like the brain. So it's made up of thousands to millions of individual nodes, and each one of those nodes communicates with all the other nodes. And the principle is to try to maximize the number of correct answers. And so in the similar fashion to iterative reconstruction that you'd be all familiar with, is it compares an estimate or a guess at the start to a known outcome. It actually adjusts its learning based on an error between what its guess was and what the actual grounded truth is. And often that reference grounded truth might be a human report, or it might be a other form of gold standard. And so what it then does is it adjusts the weightings of the different nodes to produce a different estimate. And I'll show you that schematically in a second. And so you end up with thousands to millions of different iterations through the process as the neural network learns to identify the features and weight those features. Okay, so I'll again talk about that in a second. And so the more data and learning that goes on, the better the inference phase of the process. And so this is, leads us into the process called deep learning. So the emergence of machine learning in the imaging environment, obviously the literature and competence around medical imaging and nuclear medicine in particular has seen a whole bunch of machine learning and deep learning and artificial intelligence papers and presentations emerge. And this is associated with improved algorithms, better hardware associated with microelectronics, importantly the availability of big data, and you need that big data for training of these systems, and the impact of radiomics, which I've already sort of outlined. And so that, recognition and refinement of radiomics has sort of laid a platform for the emergence of that machine learning and then subsequently the deep learning. So machine learning itself is a tool for analysis of outputs and quantitation and the radiomics itself. And deep learning uses neural networks to then analyze the images themselves, and it sort of like does it in the same way or a similar way to the human observer. So machine learning is really about that convolution aspect of things, providing that analysis of the outputs, including the radiomics and our standard quantitation. Whereas deep learning takes that deeper dive or that extra step into trying to analyze the image features themselves, like we would with a standard interpretation. So the hierarchy of artificial intelligence, artificial intelligence itself is all encompassing. Everything sort of fits into that. And so the next, little domain under artificial intelligence is this area of machine learning. Under that you have representative learning, and then within representative learning we have these neural networks. And the neural networks are what actually then gives us the opportunity for a deeper learning. And then within that deep learning framework, we can actually have convolutional neural networks. And that's the language that we'll be using over the next few slides. So this is a schematic that I've developed just to try to, and it's a simplified version, so forgive me if this is too simple for you. But it's just to try to give, for the novice, an understanding of what actually happens behind the scenes with these neural networks. So, and I've simplified it with just a few nodes. But we actually have a large data set, so a large n number of images. And for all of these images, that we actually have a gold standard, a grounded truth. So we know what they are. We know whether they're normal, whether they have epilepsy, whether they have dementia. We know what the actual finding is, and we know where it is. So we know it's epilepsy in a certain location, or we know there's certain perfusion defects or metabolic defects in specific locations. And so within our nodes, so all these circles are our nodes, and you can see that all the circles are connected to the other circles, so the nodes are interconnected, and we have an input layer, and this is where this data comes in. And so in here we've got a 3-node input layer because we're saying there's only 3 features. There could be 100 features, but we're going to say there's 3 features. And so within that node, those nodes, they communicate with the next couple of layers, which we call hidden layers. And those hidden layers are where all of the hard work goes. That's where the thinking happens. And so we have a guess. So we have an input of an image. It actually has a bit of a guess of whether there's disease or whether there's not disease, what that disease is and what the pattern is. And that comes out through this output layer and gives us a determination. So let's say that in this particular case, it tells us on the first iteration, it tells us that this scan is normal. But we know the grounded truth is that the patient has epilepsy. So it actually has an error. And it measures that error. And it refines it. So then it comes back through the neural network. And what it does is actually adjusts its weightings on each of these individual nodes. And so a simple way of looking at it is that, node 1 over here in the input layer may have actually had equal weighting as node 2 and 3. And what we need to do now is go, well, if we gave everything equal weighting, is that we end up with the wrong answer. So maybe we need to weight feature 1 more heavily than feature 2 and 3, and that might give us an answer that's closer to the truth. So then it goes through another iteration. Again, it might say, well, it's abnormal, but we're going to call it dementia. And so we go through another error, and it makes another adjustment to those nodes. And not just the input nodes, but all of the nodes in the system get a weighting adjustment to try to actually end up with a better interpretation. So what ends up happening through this training zone is that you can go through thousands of iterations and many image files against many grounded truths. And so you're teaching you're teaching the artificial neural network how to interpret that data set. And it might be not just as simple as saying normal or abnormal, it might be actually defining specific features like where that abnormality occurred. So once you've actually trained it, you can then test it. So you give it some blind data so that you know the answer to, and you test it and you go, okay, well, you know, the neural network got 100% of them right. So now we can actually confidently then use it in our inference phase, which is when it actually makes predictions on real patient data. So once you've actually trained that neural network, then you actually have your small population, so your ongoing patients, you enter that data in, and it might be that instead of having 3 features, you're only using 1 feature or 2 features, but typically it's going to be 100 down to maybe 5 features through the architecture of your hidden layers, and then having your diagnosis coming out the other side. So this is a diagram that comes from the latest Journal of Nuclear Medicine, and essentially looking at machine learning in nuclear medicine. It's the first part of a 2-part series, and it just summarizes what I've already covered on the previous slides, but adds this additional convolutional step. And in some ways is that the convolutional steps that you can see in here with the pooling steps is part of that radiomic process. Where you're actually extracting those features and then feeding those into a neural network. So how is that sort of system used? It's not just for diagnosis, for another number of things. So if we actually look at the models that are being used for artificial neural networks, the existing model would be that you had a population, a number of imaging tests, a radiologist or nuclear medicine physician would report the data, it'd be positive or negative, and I know that that's a simplification, but you get the meaning. That's how things are done now. So a neural network can be used to triage patients. So you have a population, the imaging test, and then the first thing that happens to the artificial neural network, it actually interprets every bit of data that comes through, and it will identify patients who may have an outcome of urgent nature. So it identifies the patients that need to be pushed to the front of the line for reporting, and they head off to the radiologist or nuclear medicine physician for more urgent reporting. It doesn't mean the ones that the artificial intelligence doesn't identify don't get reported. They just may get reported in a less high priority fashion. That's actually a pretty useful use of artificial intelligence. The one that everyone's scared of is this replacement model where the artificial intelligence does the reporting and there's no need for a radiologist and nuclear medicine physician. Well, that's not going to get support. It's probably not going to be trusted, and I don't think that that's actually got legs in the current environment. And then there's the add-on model where the radiologist does their reporting. If it's positive or it's negative, then it goes to the artificial neural network, and that artificial neural network actually adds on additional information. It might actually double check it. It might be used just for gaining a bit of confidence. Me personally, I think that we can actually integrate all those into one model. So we have our imaging test, and what our imaging test does is that it actually, in parallel, gets interpreted by the artificial neural network, which will prioritize or triage patients to the radiologist or the nuclear medicine physician. I think that's a really important step, but also does some pre-analysis and data extraction. So it extracts some features that are particularly important for the radiologist before they do their report. And then, of course, those are passed on to the radiologist or nuke med physician for reporting. And then the artificial neural network and the radiologist independently decide whether the study is positive or negative. If, as depicted by the blue arrows, that the neural network and the radiologist are in agreement, whether it's positive or negative, well, then that confers a degree of confidence in the outcome. Whereas if there's a disagreement, as depicted by the green or the yellow arrows, well, then it actually is a bit of a trigger to then come back and actually have a second look at the interpretation to see, where either the artificial neural network or the radiologist, nuke med physician may have overlooked something. And I think that's a really solid model. So in radiology, and machine learning can be used to determine which of the enormous number of extracted features in radiomics can be used in either isolation or in combination. Right, so you don't have to deal with 250 individual features. the machine learning can actually identify the features of most interest. It also highlights any relationships that have not been considered in the semantic or radiomic analysis. And if you've got 250 features, it's very difficult for the human mind to be able to actually look at the correlation between all those features. In fact, is that some reports would suggest that you can only deal with 7 at a time with the human brain. So the machine learning adds a layer of understanding that the human brain can't do. So some specific machine learning targets: automated image segmentation, lesion detection, references to historical images, so you know how things have changed over a sequence or series. Generating reports, so a list rather than a narrative, like a narrative might come from the reporting physician, but provide a list type generation for report, which is perhaps useful as a second reader for reports. To error detection, assist with data mining for research as well as to feed into radiomics. It can be used for business analysis in real time, so workflow, quality improvement, a number of outcomes and performance measures. And of course, one of the important things is that it may actually improve our detection of incidental findings. And I reference the research around gorillas in our midst that some of you may be familiar with, but I'll discuss in a slide or two. So I thought it was a slide or two. It's actually the next slide. So gorillas in our midst was a Harvard experiment that was actually really interesting around sustained inattentional blindness. And what it essentially means is that if you're really focused on seeing something, you won't see other things that are even, you know, that are apparently very obvious. So in this task, an observer was asked to, well, a number of observers were asked to watch a video of these group of people passing a ball, and the idea was you needed to count the number of times the ball was actually passed. And because people were concentrating so intently on counting the number of times the ball was passed, majority of people didn't notice that someone in a gorilla suit walked through the middle of the scene. Okay, so that's sustained inattentional blindness. So it makes sense that someone came along and actually took that to the next level and embedded this beautiful little artifact of a gorilla in a series of CT images of the chest. And so for us, you know, I've highlighted it. It's pretty obvious. You can see that it's there. It shouldn't get missed. But 83% of expert radiologists reporting this data set, and they didn't just get shown one image, it was actually a complete set of chest slices. But 83% of expert radiologists didn't see the gorilla. And interestingly, 60% of those that didn't see it looked directly at it. So the image on the right with the blue dots on it is those blue circles are actually the eye tracking that they did on the radiologist doing the interpreting. And so you can see that quite clearly that 60% of the radiologists actually looked directly at the gorilla but didn't actually notice it. And so this idea of sustained inattentional blindness in expert observers means that an expert is less likely to see something that's like incidental because they're not looking for it than someone who is actually just an amateur having a bit of a look. And so there's a real role for artificial intelligence in picking up these sort of incidental findings. And this is just an example of inattentional blindness that we experience in nuclear medicine. You can actually see that this is a study by Skillen back in 2012. It was published in the JNMT, and the arrows show areas of brown fat that have disappeared in the same patient between warming the patient, so using patient warming to reduce brown fat. You can see on the far right, in a similar paper by Garcia in 2010, again showed that warming the patient would reduce the amount of brown fat. But that inattentional blindness means that we probably haven't noticed the heart, and certainly it wasn't reported in the Garcia paper and previous papers. But when you actually look at the heart, the cardiac uptake, then you can actually see that there's actually a decrease associated with warming in the heart as well. So further study done by O'Loughlin actually managed to map that with FDG and demonstrated that there were seasonal variations associated with the ambient temperature over a 3-day period, not necessarily during the uptake period, that actually shaped the amount of uptake in the heart, and that linked back to seasonal variations in cardiac event rates and further, it also influences and explains some of the variability that we saw in a different project associated with iodine 123 MIBG uptake in the heart, which was also influenced by the temperature. So this is actually something that, using feature extraction and tying that with artificial intelligence, that you may just actually see that these sorts of things that we might miss because we're not looking for them. We're looking for brown fat, or we're looking for tumors, and we sort of overlook those incidental types of things, that an automated and artificial intelligence type extraction of features and identification of features might actually overcome that. So that brings us to neural networks. I've already given you a bit of an insight into how the neural network works, but they're not new to nuclear medicine. They're widely used in research modeling. Back in 1993, Scott and Palmer used it for VQ interpretation. They had 28 input parameters, not a lot, 28. They had a single hidden layer with 15 nodes. And what they did is they used 100 VQ lung scans that had angiographic correlation, and then tested it with 28 new cases. And what they actually showed is, after they trained, so the 100 VQs were the training phase, so they trained the neural network interpreting with known angiographic correlation on those 100 studies, and then they introduced 28 new cases that the neural network hadn't seen, and compared that to an experienced physician, and actually showed that compared to the gold standard, that the neural network was actually superior. And then later work by Scott in 2000 actually compared the neural network, again in lung scans, to 3 physicians, and the neural network was shown to be superior to 2 of those physicians, and those physicians had 15 plus years of experience, and comparable to the third. So it's kind of exciting that these things could be used as double reader technology. Neural networks have also been used to analyze myocardial perfusion scans. It extends that radiographic feature extraction, assists further a deeper look at the quantitation and how the quantitation is used against other bits of features, or features that have been extracted from the data, like the defect scoring, in this particular case using the 17 segment model. And so what it actually showed, that comparing it to 6 expert nuclear cardiologists in a very, very large number of trained studies, so 5,685 regions, so that's not patients, that's regions. So divide that by 17 and you've got your number of patients. That was used for the training. And then when they tested it, it actually showed that the neural network was superior in terms of defect scoring. And that doesn't mean it's superior in the final outcome and diagnosis, but in the process of actually doing the defect scoring, that the neural network was superior to the 6 expert nuclear cardiologists. And then that was shown in the ROC analysis, and the ROC analysis is a fantastic way of actually comparing one approach to another, because you can actually just measure the total area under the curve between 2 approaches. And so you can see here that the scoring of the 6 nuclear cardiologist versus the artificial neural network for the stress defect, the rest defect, and then determination of ischemia. In each case, the area under the curve was superior for the artificial neural network. Not a lot of difference, but certainly superior. Again, in publications more recently, we've seen some data in 2,619 patients where machine learning was used to better predict major cardiac events. It was less successful in determining or predicting the time to event, but it was actually shown to be an improvement in the prediction of a major cardiac event. The same authors, in a recent publication in the Journal of Nuclear Medicine, again 2019, and this was ahead of print at the time of this presentation being put together. They actually showed that a step further than the machine learning, looking at artificial neural networks, and in particular the convolution neural network that you can actually see represented there with the feature extraction, so that radiomic aspect of feature extraction using the convolutional layer, and then the pooling step before all that data is fed into the neural network for a deep learning model. And what it actually showed was that it had improved automated interpretation. Now, this is actually an important step, because what it's really doing is saying that, the total perfusion defect scoring using things like polar maps, so we're talking about an automated or an artificial intelligence system, can be enhanced by adding the neural network to it. It's not actually saying that it's actually improving the diagnostic outcomes from the nuclear medicine physician or nuclear cardiologist's interpretation. What this data was actually showing was an improvement in the risk stratification compared to the automated detection. And that's best represented looking at the area under the curves. The two sets of data on the left with the A data is looking at per patient, and then per vessel on the right, or the B data. And essentially, even though the lines are fairly close, there's a significant improvement in the area under the curve, which just indicates that there's a better outcome or better predictive capability than comparing it to the total perfusion defect scores. So I think in the future what we might see is some data like this, and this comes from the same paper ahead of print in 2019 in the Journal of Nuclear Medicine. And it just sort of shows the standard output that you might get from your quantitative software for polar maps, and with the addition of this additional polar map that dovetails with the total defect score, or the total perfusion defect polar map that you can see there. But with a neural analysis or a convolutional neural network output that actually has a polar map that shows the probability of disease. And this might better predict events in the future. So I think this is the way that we'll be moving forward. We're already using a little bit of artificial intelligence in terms of the development of those polar maps and the predicting events. But I think to go that step further and start to integrate the artificial neural networks into those quantitative programs, and then being able to display that in some simplified form like this polar map will be a huge advantage. So a quick snapshot. In France, they've used deep neural networks to circumvent PET-CT radiomic feature selection for lung cancer. So if we don't think radiomics applies to nuclear medicine, it does. Okay, and we can actually use those neural networks to actually look at the huge raft of PET and CT based features that can be extracted, rather than actually doing it manually. At Yale, they employed a shallow neural network for dose reduction in brain PET. It's been used for deep convolutional neural networks to automate lung tuberculosis classification, and that had an area of under the curve of 0.99, which is near perfect. And then they've trained deep convolutional neural networks to discriminate between solitary cysts and soft tissue lesions on mammogram. Area under the curve of 80.8, which is not as impressive, but still fairly effective. And then, of course, convolutional neural networks have been used for automatic detection of risk fractures, and particularly useful in pediatrics. So you can see there's a very large training set of 7,356. They tested it on 524 and showed 98% sensitivity, 73% specificity. So sensitivity is good, specificity needs some improvement. So for me, perhaps the greatest and immediate value that comes from neural networks is in looking at radiomic feature extraction. So which ones, not only extraction, but selection. So segmentation and then selecting which features are most important. So providing that selection process, and in particular in higher order studies like SPECT and PET, where those radiomics are important. But I think that there's also a value in assisting in the interpretation phase in those lower order studies that we might do, like the bone scans, lung scans, renal scans. Probably less so in terms of interpretation in higher order studies like SPECT and PET. But any real value needs big data, and we don't have the big data, to be fair. So let me give you a little data case example, and let me show you where probably it sort of fits in and how we can use big data to improve. So this is one of my PhD students, physician in Pakistan, who looked at iodine 123 MIBG from a regional perspective. Is that when we actually use MIBG in the heart to, predict event rates or identify who might benefit from ICD, we tend to look at it globally. So we look at the global uptake, global washout. But if someone has a myocardial infarction, particularly large myocardial infarction, well, you're actually going to get delivery uptake on the early phase, you're going to get delivery, and then you're going to get washout associated on the late phase from that myocardial infarction. And that's what we'd expect. And so that will actually give you an artificially high washout rate. And so from a global perspective, it doesn't really make sense from a precision medicine perspective or a personalized medicine perspective to actually look at it in a global fashion. So we looked at regional analysis, and the research was sponsored by ANZSM. So if we actually break it down into steps, the patient data, age, gender, New York Heart Association classification, their clinical history, and we do some functional imaging. So we're looking at left ventricular ejection fraction from the rescated heart pull scan, cardiac MRI or echo. And essentially, New York Heart Association classification of 2 or 3 with an LVEF less than 35% means that in Australia, people are eligible to get an ICD, $10,000 a pop. But 67% of patients that die of sudden cardiac death who would have benefited from the ICD occur in patients that have an LVEF greater than 35%, so would be ineligible. And then 33% of heart failure patients with an LVEF, that should be an F, not a H, greater than 35% also die of sudden cardiac death. So it's obviously an ineffective model, and certainly not what you would call precision medicine. But this is the way that we actually try to do personalized medicine. We're actually looking at the patient's individual circumstances, and it's a patient-facing decision, not necessarily with the best of outcomes. So we introduce our metabolic imaging, and that then goes from this personalized medicine to an evidence-based protocol, and we're looking at the heart to median stadium ratios. Unfortunately, there's a big range in the literature from 1.6 to 1.85 in terms of 2-year survival, and then global washout is probably the strongest marker. But there's a number of variations that that impact that, which is probably for a later discussion. But this is where we'd have our evidence-based but we want to do precision medicine and improve outcomes. And so what we stepped up and actually said, well, let's look at the SPECT regional uptake, what the washout is from the regions that are immediately adjacent to the area of myocardial infarction, and use that to predict patients' likelihood of having an event. And it turns out that patients had 0 cardiac events in the follow-up period if they were identified with this regional approach as being not at risk of having a cardiac event, which is actually pretty good. So for us, we improved our outcomes, and some of those patients were eligible for ICD that elected not to have them and are event free. So what's the next step? For us, we've accumulated this little data. So we've got little data, and little data on its own is not particularly helpful, so we want it to be big data. Just to focus on the molecular level imaging, so it's not just about this metabolic imaging, we've actually gone to that next level. So not just looking at those washouts, we're including some of those markers like telomere length and ACE genotype and BNP to go with those radiomic feature extractions. So it's radiomics combined with the other omics that we can actually provide. So we ended up with 100 variables, including those biomarkers, our regional analysis, defect scores, changes in defect scores, so 100 different variables. And as I said before, is that most of the time we can only accommodate 7 in our decision making mentally. And it turns out that washout greater than 40% on the SPECT study, looking from a regional perspective in the non-infarcted myocardium, was associated with an 11 times higher risk of having a cardiac event. So we were kind of excited about the predictive potential. And even more excited, I was to say, well, let's see what an artificial neural network can do to streamline that process, so we're not dealing with 100 variables. So, and it's truncated on the left, that's your input layer. There's over 100 individual variables that are your input layer. The binary target will be a cardiac event or no cardiac event in the follow-up period. 2 hidden layers of 6 and 5 nodes respectively, using a logistic activation function, the weighted square error method, and a quasi-Newtonian training method. Turned out that following the training method that there was fairly robust validation of 0.998, and so as a result of that, we're actually fairly confident with our final architecture. And so you can imagine you've got 100 inputs. What do you think our final architecture is? Just 2 inputs. Okay, so despite those 100 inputs and the results that we actually got from our normal analysis, it showed that there were just 2 inputs of importance. Now the sensitivity was only 50%, which means that that the neural network is suggesting that a 1 to 2 year follow-up is not in the original data is not long enough to predict long-term cardiac events, and rightly so, but 100% specificity. So it predicts an event, there's going to be an event. Washout was the senior partner. And this is really interesting because washout, it's planar washout. It's not regional washout. It's planar washout. It's going back to the old school. The whole purpose of the study was to actually say, well, it makes sense that regional washout is more important than planar washout. Now, this doesn't mean that regional washout is not important. It's just saying that there is such a close correlation, going back to that heat map we described earlier, there is such a close correlation between the planar washout and the regional washout that if you include them too, you actually weaken your overall outcomes, and that planar washout has a higher degree of predictive capability than the regional washout. And especially when that is combined with a change in LVEF. So what the neural network has done is it's identified the 2 features from our radiomic extraction, our feature extraction, that should be considered by the physician when they're doing their semantic reporting. It's a powerful tool. So it's pretty simple. It shows that a change in LVEF from baseline to some point later of 10% or more, combined with a planar washout of 30% or more, is a high risk of cardiac event. In fact, 100% of those patients will have an event over the subsequent 2 years. And so it comes down to this Occam's razor, right? Is that sometimes the simple solution is not necessarily the best, but it's certainly the easiest one to exclude and probably the point to start. The best part about this is it's programmable. Okay, this can be exported as a simple Python language that can be built into a mobile phone app or a computer app that you actually can just put in these features. So you enter the data in, and you can use this app to then predict a risk of cardiac event or risk of diabetes or risk of heart failure or anything else. That if you're using these sorts of neural networks, that you can then create these programmable apps, which might have a really important use in remote health scenarios. So future opportunities. If we think about that neural network and some of the things that are confronting nuclear medicine, is that CT is fantastic for co-registration, attenuation correction. Not all SPECT studies are done with CT. Most PET studies are nowadays, but we can actually look at patient radiation dose reduction. So we can end up with a PET or SPECT, a large number of non-CT corrected PET or SPECT data, enter it into a neural network, have it estimate what the CT would be, actually validate that against the actual CT that was collected, have it learn, go through that 1,000 iterations, thousands of studies to learn how it weights those individual nodes to come up with the correct CT. And then there's a possibility that we can actually be doing PET or SPECT with no CT, and the neural network actually for each individual sinogram generates a pseudo CT that can be used for attenuation correction in the reconstruction process. Now, it's probably not necessarily likely that we're going to do that on standard SPECT systems, but certainly some of the newer systems that maybe solid state detectors that don't have the CT attached to it, that perhaps there's scope for using these pseudo CT scans. The other, probably more important application of it is for PET MRI. So when we actually have PET MRI, we lose that CT scan. We've either got to have a CT scan done somewhere else that we then co-register and use. But we might actually be able to train a neural network on the PET MRI data, have it guess what a CT would look like, and the MRI part of it would be combined with the PET, would be very informative in terms of the accuracy of a pseudo CT. Actually have a CT scan that it actually compares to and learns against. So you go through a training phase, and then in the future what that would allow you to do is actually use a neural network for it to develop a pseudo CT scan with a high degree of accuracy for PET MRI scans without the need for another CT scan, and providing attenuation correction that is superior in the reconstruction process. So I think that's kind of exciting, and it's reducing that radiation dose and of course the cost of resources. Summary. What are we doing? What are we ready for? Where are we at today? So we have a population, we have our imaging tests, and in that process, largely what we do is we do our semantic our nuclear medicine physician reporting. We do actually do radiomic feature extraction, but it's done manually by the humans, or as part of our, sometimes we have software like QGS or other automated software that spits out some radiomic features, and the physician needs to be able to interpret that. So that extraction is done by the physician. So we have this opportunity to actually perhaps enhance that. So we do the red part already. We do the blue part. So the blue part is certainly precision nuclear medicine. Improved outcomes is part of that process, driven by the red arrows. But I think that if we can add the green over the coming decade, that we actually see an emergence more strongly of the green arrows, then the part of the schematic represented by the blue arrows will be significantly enhanced. So we're going to enhance precision nuclear medicine by instead being able to actually use radiomic feature extraction using a neural network, using learning and big data to inform those radiomic feature extraction processes. Not just the segmentation, so segmentation being automated, but actually determining which features are the most important that should be weighted in the semantic physician interpretation. So I think we can use that to improve our accuracy, reduce our costs, improve our efficiency, and create that degree of automation. But it needs these big data privacy issues to be overcome, and of course the communication that comes with that as a profession. So we end up with a simpler process, a faster process. The confidence of the physician in the semantic process is improved, and the outcomes for the patient is improved. And that brings us to the end of the presentation. I just wanted to finish by introducing the annual scientific meeting of the ANZSNM in 2020. It's actually the 50th annual scientific meeting, so it's a big anniversary year. And so it's a special event for all of us. And being in the year 2020, it affords the opportunity for us to actually stop and reflect on where we've been. So having this sub-theme of 2020 hindsight, we can look at historical insights, those things that have got us to the place where we currently are, scope of practice, but also celebrate the legends and the giants that have got us to where we are. And the other side of that being 2020 vision, where we actually cast our eyes forward, looking at those future insights and future developments, advanced practice, and celebrating the emerging leaders of our profession, which are amongst us all. Our central theme is local innovation, global inspiration. We have an enormous program of fantastic speakers from Australia and New Zealand, from Asia, from Europe, and from the US and Canada. So we're very fortunate to have a really solid program. Our 6 main speakers are listed on the screen, as you can see there, with Professor Daniel Berman and Professor Wim Oyen, Professor Lionel Zakia, Professor Eric Rowan, Professor Rand Klein, and Professor Vaskan Dilzen. So some really good speakers are in the main 6. But they are supported by a cast of just amazing local and other international speakers that there'll be more detail on the website. Please take note of the Twitter, the Facebook site, and of course the web address for the conference. We'll be actually posting information about sponsors, about speakers, about the program, and other events around those regularly throughout the next 12 months. So follow those to stay abreast of what's going on. The program itself will be at the International Convention Centre. It's a 3-day program, and it's a solid 3 days. So it goes from the pre-conference symposium on the Friday, starting in the morning, with a focus on radiomics, artificial intelligence, deep learning, big data, and the interconnection of those with our precision medicine and precision nuclear medicine in particular. And that will actually be our pre-conference symposium in the theme of an intelligent imaging summit. We'd hope that that would actually be something that we continue annually, so having this Intelligent Image Summit each year moving forward. Later in the afternoon on the Friday will be the opening plenary, which will feature 3 amazing speakers, and that will be followed by the welcome reception and the dinner for AANMS and the technologist party. Saturday happens to be Anzac Day, so we'll do a few things like I'll organise for transport to dawn service for those that are interested. Try to organise 2 up during the morning tea break, but there'll be multiple plenary sessions, feature lecture sessions, the Lowenthal lecture, Pioneer lectures, special interest group sessions, award sessions, posters, and of course finish that night with the gala dinner, which we'll celebrate as a Legends dinner. The Sunday's not a half-day program or a 3/4 day program, it's a full day program. Starts and finishes with plenary sessions, has some feature sessions in the middle that include some, again, some of our key local and international speakers. There'll be specialisation sessions and streams for the various specialisations. Again, abstract presentations, posters, the close, the introduction of the 2021, and then later that night we'll have a reunion dinner for universities of Sydney, Charles Sturt University and Newcastle alumni and faculty. So it's an exciting program. As I said, I encourage you all to review and tag the Twitter account, the Facebook account, the website. Keep those dates in your diary. Think about early registration and submitting your abstracts to what will be an amazing 50th anniversary get together for our profession.